Kinetic energy is just one side of the coin. The other side of the coin is the so-called potential energy. The next couple of minutes will thus be dedicated to study in detail what this energy is in the context of gravity. We will start the study with these two seemingly different problems. The first question is, a ball of mass m is dropped from rest at the height h above the ground. Ignoring air resistance, compute the kinetic energy of the ball just before it reaches the ground. Whereas the second question is, a ball of mass m is thrown upward. Ignoring air resistance, compute the work done by gravitational force on the ball to reach the maximum height h above the ground. Both involve a ball of the same mass m, covering the same height h. The difference is, in the first question the ball is going down, in the second question the ball is going up. Like what people like to say, the two questions are same but different. Let's start with the first question on the left. To compute the kinetic energy at the ground, one will need to know the speed of the ball at the ground, or to be more exact, the speed of the ball just a moment before it hits the ground. This speed can easily be computed because the ball is free-falling with constant gravitational acceleration g. As the problem indicates, it starts from rest, which means it has a zero initial speed and it has to cover a distance h just before it reaches the ground. We can compute the final speed using one of the equations from the accelerated motion model, and we can then compute the final kinetic energy of the ball given by mgh. Because the ball starts from rest, its initial kinetic energy is zero. Hence, mgh is also the expression for the change in the kinetic energy of the ball. Keep this in mind while we turning our attention to the second question. Work done on an object by a certain force, as we just learned in the last lecture, is given by the force multiplied by the displacement multiplied by the cosine of the angle between the force and the displacement. In the context of this problem, this translates to minus W times h. Since we are computing the work done by gravity, obviously the force of our constant is weight or gravitational force. By the way, I use capital W sub g to denote work done by gravitational force, where W is to denote the force of the weight itself. The displacement is obviously the height h that the ball covers, yet most interesting and important is the negative sign. I explained to you in the previous lecture under what circumstance a negative sign appears in the computation of work. Let me explain that one more time here, that it appears because the force opposes the displacement. Weight always points down, but the ball is being displaced in the upward direction. It is thrown upward. Since we know that weight can be written as mass times gravitational acceleration, we arrive at the final result of work done by gravitational force is given by minus m times g times h. But, wait a minute. Do you see what I'm seeing? Do you see anything weird here? The answer from these two seemingly unrelated questions differ only by a negative sign. Is this coincidental, or is there something deeper? Well, nothing in this lecture is coincidental. Through these two examples, I would like to bring into your attention one of the most basic and important premise in physics, the conservation law of energy. But before we go into that, let's denote mgh as the expression for gravitational potential energy. The letter capital U is used to denote this potential energy, and the subscript G is used to indicate that it is the potential energy pertaining to gravity. In the context of the second problem, because potential energy at the ground is zero, because h is zero at the base of the tower, by definition, the change in the potential energy of the ball is equal to the potential energy of the ball at its maximum height itself. With this in mind, we can write the relationship between change in kinetic energy delta K to the change in potential energy delta UG compactly. The change in kinetic energy is equal to the negative change in potential energy. Let me repeat. The change in kinetic energy is equal to the negative change in potential energy. This means if kinetic energy increases, potential energy decreases. Vice versa, if kinetic energy decreases, potential energy increases. If we get back to our illustration of the basketball and leaning tower of Pisa, now that we are aware that the two problems I presented earlier are somewhat related, I will put them together in a single illustration as shown here. It starts with the ball at the ground. The assumption remains the same. We can ignore air resistance and gravity is the only force at play. The man thus provides the initial speed that thrusts the ball upward. Because of gravitational pull, the ball will slow down. We say gravitational force is doing negative work on the ball. As the ball slows down, its kinetic energy decreases, but its potential energy increases as it gains height. If the speed v that the man provides at the ground is equal to square root of 2gh, the ball will be able to reach maximum height h, and hence maximum potential energy mgh is attained. In the same situation as projectile motion, when the ball reaches maximum height, it will stop momentarily there. Gravity has slowed down the ball to zero speed, hence its kinetic energy is also zero at this stage. Whatever goes up must come down. This time around, gravity is doing positive work on the ball and speeding the ball up as it is falling down. Its kinetic energy increases as its potential energy decreases as it is losing height. And if there is no friction or air resistance, I emphasize this assumption once again, if there is no air resistance or friction with the air, then the ball will reach the ground back at the exact same speed of square root of 2gh as when it was released. The kinetic energy of the ball at the ground is back at mgh, and its potential energy is zero, just as when it started. So you may think of this whole process as energy is being converted from one form to another. Kinetic energy at the ground is converted into potential energy as the ball goes up, and potential energy is converted back to kinetic energy as the ball goes down. Yet something remains constant. This something is the expression of mgh. Because mgh remains constant or conserved, therefore the whole process is symmetrical. It decelerates as it goes up and accelerates as it goes down by the same rate, which is g. It takes the same amount of time to reach its maximum height from the ground as the amount of time for it to reach the ground back from its maximum height. If it is propelled upward at the speed v from the ground, it will reach the ground back at the exact same speed v. If you recall, it does sound like projectile motion, but with no horizontal component. Now we can surely come out with a better name to refer to this expression of mgh than to call it something. This something is called mechanical energy, denoted with E subscript m. Mechanical energy is the sum of kinetic and potential energy. By the way, allow me to digress a little. It is clear why kinetic energy, from the name of it, is associated to the motion of the object. But do you have any idea why potential energy is called as such? Well, if kinetic energy sets the world into motion, potential energy refers to the energy that an object could potentially convert into kinetic energy or work. Work and kinetic energy is related by the work energy theorem, remember? When the basketball is brought up to the topmost level of Pisa Tower, it gains potential energy. But this energy has no practical use. It remains a potential until the ball is finally released and the potential energy is converted into kinetic energy. And we can finally derive a useful work out of it, perhaps to drive a pole to the ground as shown here. Potential energy is not only limited to gravitational potential energy. There exists potential energy pertaining to elastic force, which is called elastic potential energy. We will learn how to compute it during our face-to-face session. There is also electrical potential energy, which comes from the attractive repulsive force of electric charges. The adenosine triphosphate, or ATP, in your body is a form of chemical potential energy. It could potentially be converted into kinetic energy or useful work that sets your muscle into motion. Getting back to the equation, we can further simplify the expression of delta K equal to minus delta U into delta E equal to 0. If delta E is equal to 0, that means there is no change in the mechanical energy of the ball throughout the process. We say mechanical energy is conserved. In the context of our problem, this mechanical energy is given by mgh. The mechanical energy of the ball is mgh at the ground, but this mgh is purely contributed from its kinetic component, and the mechanical energy of the ball is also mgh at the top, though this time it purely comes from its potential term. In between, the kinetic and potential energy of the ball vary in time. When one increases, the other has to decrease. Nonetheless, when both are summed, the total will have to be given by mgh, which is conserved. Allow me to repeat that again with the aid of this illustration. The ball is released at speed v0 to reach the maximum height capital H from the ground. First thing first, it is obvious that v0 and h are related by this equation. Now, often we are concerned with the motion of the ball's rod, not just what happened to it at the ground or at the maximum height. As the ball goes up or down, speed and height vary in time, and so do kinetic energy and potential energy as a result. The changes in kinetic and potential energy are constrained by this equation. From this, relation between speed and heights, and hence relation between kinetic and potential energy at different time can be established. The sum of the kinetic and potential energy at different time itself is fixed. It is equal to the kinetic energy of the ball at the ground, which is also equal to the potential energy of the ball at maximum height. All are equal to the total mechanical energy of the system. That is the conservation law of mechanical energy. But remember, there is one subtle thing we always tend to miss. That is the assumption, namely the fact that we are ignoring any sort of resistance or friction from the air. It is very important, very important. For were we to consider air resistance into the calculation, which we realistically speaking should, then mechanical energy is not going to be conserved. You can imagine the effect of air resistance to the motion of the ball when it goes up, for instance. Air resistance will slow down the ball, causing it to attain a maximum height less than h, even though the ball is shot upward at the same speed v0 from the ground. Similarly, air resistance will slow down the ball as it falls from the height h. As a result, it will reach the ground at a speed less than the square root of 2gh. Resistance or friction dissipates mechanical energy. Mechanical energy is no longer conserved in the presence of air resistance. We will discuss this in more details in our next lecture on conservative versus dissipative force.